Welcome to Complex Analysis, Lesson 22. In this short lesson, we're going to show how to take the integral of a real rational function that's comprised of trig functions. So I've showed the problem here. So f is a function of sine theta, cosine theta, and it's basically a quotient of various combinations of these two types of trig functions. And we're going to use residues in order to solve the problem. So we're going to use residues to determine the integral, or should I say the antiderivative, of rational real functions with real coefficients comprised of trigonometric functions. So we're basically looking at something in this form here. We're going to take the antiderivative and then evaluate the integral. And the function itself is various combinations of sines and cosines. And you can also have a quotient, which is why I use the term here, rational real functions. That just means a fraction of different trigonometric functions in this case. So we're going to make some substitutions. To solve the integral, we first convert the above integral into a complex contour integral over the circle modulus of z equals 1. So that's a circle centered at 0 and has radius 1. And we let z equal e to the I theta, where theta is between 0 and 2 pi. And then if we take 1 over z, we get 1 over e to the I theta, which is e to the minus I theta. And then we're going to rewrite the cosine and sine of theta. We have here the cosine of theta equals e to the I theta plus e to the minus I theta over 2. This follows from Euler's formula. If you plug it in for both of these expressions, the signs will cancel out. You'll just be left with 2 cosine theta, and then you divide by 2. So this, in turn, we put back our z here. We get 1/2 z plus 1 over z. And then we do the same thing for sine of theta, and we get this expression here. So what we're going to do is plug those into our function, replacing the cosines and the sines with the complex variable z. We also need to replace the d theta here, and we can do that. We have the derivative of z with respect to theta is using the chain rule is I e to the I theta, which is I z, and we can rewrite that as bringing the d theta on to the right, and then dividing by I z, we get 1 over I z dz equals d theta. So we're going to need this. Let me circle these. We're going to need this substitution and this substitution and this substitution into our formula here for the for cosine of theta, for sine of theta, and then d theta. So let's see an example with these solutions being made, and then we'll take the integral and show how we can use residues to actually evaluate the integral. So let's take an example where we use the technique from the previous slide. We have a rational function in terms of sine and cosine. We make the substitutions we talked about. We put in 1 over 2i z minus 1 over z for sine, and 1/2 z plus 1 over z for cosine, and then 1 over iz dz for d theta. Notice that the I here and the I here cancel. We bring the 2 into the denominator, and we get 4 plus z plus 1 over z. So we have this here. Then we multiply the top and bottom by z, and we get z squared minus 1. This becomes 4z plus z squared plus 1. This thing in here. And we still have the 1 over z. So we notice that we have 3 poles, 1 and 0, and then if we use the quadratic formula, we have a pole at minus 2 plus or minus the square root of 3. However, we're taking the integral over the modulus of z equals 1, so only 0 and minus 2 plus the square root of 3 fall into this, within this contour. All right, so we need to continue on the next slide using residues to evaluate the function at these two singularities. So we compute the integral using Cauchy's residue theorem. What we have from the previous slide, just carrying it over, we started with this here, sine theta over 2 plus sine theta, and we got it in the form of a complex integral. And we noted that two of the simple poles out of the 3 fell within our contour. And so we needed to evaluate the residue at 0 and the residue at minus 2 plus the square root of 3, and then multiply by 2 pi I. So the first residue at 0, it's z times f of z, taking the limit as z approaches 0, and you plug 0 in there and you get minus 1 over plus 1. Then the residue at minus 2 plus the square root of 3, you multiply by z minus this, so z plus 2 minus the square root of 3 times f of z. One of the roots cancels. This cancels with one of the roots here. And then you plug in minus 2 plus the square root of 3. And I left out the details, but when you do the computation, you get 1. Then you just come back here and plug that in, and of course you get 0 because these cancel, and that's our solution.